This result was from a series of observations as part of the JWST Early Release Science program that was looking at transiting exoplanets, so those planets that happen to pass in front of their host stars along our line of sight. And this particular planet is a planet called WASP-39b that orbits a star very similar to the Sun. It's about 300 Kelvin cooler than the Sun. The planet is on a very short orbital period. It's very close in to its host star, and this in turn means that it has a very high temperature of about 1100 Kelvin. And the other thing about this planet being so close to its star is that we expect that it's tidally locked to the star. This planet has one permanent day side, which is always facing the star, and one permanent night side that's always facing away from the star.
I imagine things cannot live on these planets, but if you could kind of look at the morning side and look at the evening side, what would each look like?
What we see evidence for is a larger degree of gaseous carbon dioxide at the hotter evening side than at the cooler morning side. And what this is probably telling us is that there is some species that is condensing out of the hotter day side gas as it passes into the night side gas, and is leading to a larger amount of clouds on the cooler morning side than the hotter evening side.
Now that you've been able to do this, are there other planets you want to look at to make sure that the result matches up?
One of the things that we'd like to do is to analyze the same planet, but over a wider wavelength range. So the results that we're presenting so far are from a single instrument on JWST that covers a wavelength range from about 2 to 5 microns. But JWST has actually observed this planet with several different instrument modes, covering a combined wavelength range of about 0.6 microns in visible light to about 15 microns in the mid-infrared. Of course, what we'd also like to do is then apply these techniques to a much broader set of planets, covering, for example, different temperatures, different masses, different radii. I guess one thing I would like to make clear is that there were other techniques that we used to analyze this data that were complementary. So, for example, the lead author approached the problem in a slightly different way. So rather than just fitting the ingress light curve independently of the egress light curve, which is what I did, the lead author's approach was actually to fit the entire light curve, but assuming that the planet actually has two different radii. So rather than being a single circle, you could imagine it as being two hemispheres essentially with slightly different radii. And so in that way, he is able to fit the entire transit without just focusing on the ingress portion and the egress portion.